Hello and welcome to Math Zone African Motives. In this tutorial, we'll dive deep into a fundamental concept in calculus, differentiating from first principles. By the end of this video, you will be able to apply the definition of the derivative to find the slope of a curve at any point, and you'll master the step-by-step process of differentiating various algebraic functions using this method. This means you'll understand where the rules of differentiation come from. So, what exactly does differentiating from first principles mean? At its heart, it means using the very definition of the derivative, which involves limits. We will use the definition of differentiation to find our answers. Let's look at the formula we'll be using. It's f prime of x, which represents the derivative or the gradient of the function, is equal to the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x, all divided by h. Let's break down this formula. It's crucial that we understand what each part means. First, f prime of x is our main objective. This is the gradient of the tangent line to the curve y equals f of x at any given point x. Second, the h term in the denominator. You might also see this written as delta x. This represents a very small change or increment in x. And finally, f of x plus h minus f of k. This represents the change in the function's output, or the change in y, as x changes by a. In other words, it's the rise of the function over that small increment h. In essence, this formula calculates the slope of the line connecting 2 points on the curve, the point at x and the point at x plus h. Then, by taking the limit as h approaches 0, we are finding the slope as these 2 points get infinitely close together, which gives us the exact slope of the tangent line at x. Before we dive into our first full example, let's touch upon a very important technique we'll be using: expanding binomials. You'll often find that the term f of x plus h requires you to expand expressions like x plus h to a certain power. When differentiating from first principles, we often have to expand powers of binomials. This is a key skill for solving these problems. Let's review a couple of common cases. First, the square of a binomial. You should remember that x plus h squared expands to x squared plus 2xh plus h squared. Remember the pattern: the first term squared plus 2 times the product of the terms plus the second term squared. This will come up frequently. Next, let's look at the cube of a binomial. X plus h. Cubed expands to x cubed plus 3x squared h plus 3xh squared plus h cubed. As the exponents get larger, expanding can become a bit cumbersome. This is where the binomial theorem becomes very useful. It provides a quick way to expand binomials for any exponent, even negative or fractional ones. The binomial theorem gives us a formula to do this. It states that x plus h to the power of n is equal to the series starting with x to the n plus n times x to the n minus 1 times h plus more terms. The important thing to notice for our differentiation problems is the pattern of the first 2 terms. We often only need these for our calculations. The key is that the first term is x to the power n, and the second term has a single h. All right, let's put this into practice. We're asked to differentiate the function f of x equals negative x squared plus 2x plus 3 from first principles. We'll follow a systematic 4-step process. Step 1 is to write down our function and the first principles formula. So our function is f of x equals negative x squared plus 2x plus 3. And our formula is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. The first step is always to set up the problem correctly. This ensures we have our objective clearly in mind. Step 2 is to find the expression for f of x plus h. This is the most common place for errors, so let's be very careful. To find f of x plus h, we replace every x in our original function, negative x squared plus 2x plus 3, with the binomial x plus h. Notice I use parentheses to show I'm replacing the entire variable. Now we expand and simplify. First, we expand x plus h squared, which we know is x squared plus 2xh plus h squared. It's critical to keep this in brackets because it's all being multiplied by the negative sign outside. Now we distribute the negative and the 2. This gives us negative x squared minus 2xh minus h squared plus 2x plus 2h plus 3. We should check for any like terms to combine, but in this case, there are none. So this is our simplified expression for f of x plus h. That completes step 2. Step 3 is to calculate the numerator of our limit expression. That is f of x plus h minus f of x. This step is about subtracting the original function from the expression we just found. We write out our long expression for f of x plus h, and then we subtract, in parentheses, our original f of x, which was negative x squared plus 2x plus 3. The parentheses are absolutely essential here. You must distribute the negative sign to every single term inside. This gives us negative x squared minus 2xh minus h squared plus 2x plus 2h plus 3 plus x squared minus 2x minus 3. Now we simplify by combining like terms. You'll notice something amazing happens in almost every first principles problem. Let's see. Negative x squared cancels with plus x squared, plus 2x cancels with minus 2x, and plus 3 cancels with minus 3. All the terms that don't have an h in them disappear. This is not a coincidence. It's what should always happen. If your terms without h don't cancel out, you know you've made a mistake. We are left with just the terms containing h, negative 2h minus h squared plus 2h. This simplified expression is our result for step 3. To verify our answer, we can use the power rule, which is a shortcut derived from this very process of first principles. Let's quickly recall the power rule. If f of x equals a times x to the power n, then its derivative, f prime of x, is n times a times x to the power n minus 1. You multiply the exponent by the coefficient and subtract 1 from the exponent. So our rule is, if f of x equals ax to the n, then f prime of x equals n times ax to the n minus 1. Now let's apply this to our original function. F of x equals negative x squared plus 2x plus 3. We treat each term separately. For the first term, negative x squared, the exponent n is 2 and the coefficient a is negative 1. So, using the power rule, the derivative of negative x squared is 2 times negative 1 times x to the power of 2 minus 1. This gives us negative 2x. For the second term, 2x, which is 2x to the power of 1, the exponent n is 1 and a is 2. The derivative of 2x to the 1 is 1 times 2 times x to the power of 1 minus 1. This is 2 times x to the 0, which is just 2. For the last term, the constant 3, we can think of it as 3x to the power of 0. The derivative is gyo times 3 times x to the power of negative 1. And anything times gyo is 0. This confirms a very important rule. The derivative of any constant is always 0. Now we combine these derivatives. The derivative of negative x squared plus 2x plus 3 is negative 2x plus 2 plus 0. This gives us f prime of x equals negative 2x plus 2. Notice that this is exactly the same answer we got using first principles. Our solution is verified. Now, let's practice with a few more examples. We'll differentiate each of these from first principles. First, we'll start with a very simple one to build confidence. F of x equals 2. Remember the process. Step 1. Write the function and formula. So our function is f of x equals 2, and we have our standard formula. Step 2. Find f of x plus h. This is a bit of a trick question. Look at the function f of x equals 2. There is no x to replace, so f of x plus h is simply 2. No matter what input you give this function, the output is always 2. It's a constant function. Step 3. Find the numerator. F of x plus h minus f of x is 2 minus 2, which equals 0. This means the change in y is 0, no matter what h is. This makes sense for a constant horizontal line. Step 4. Calculate the limit. Fe prime of x equals the limit as h approaches 0 of 0 over h. Well, 0 divided by anything, as long as h is not exactly 0, which it isn't here, is just 0. So our final answer is f prime of x equals 0. This confirms the rule we saw earlier. The derivative of a constant is always 0. Next, let's differentiate f of x equals x plus 2 from first principles. Step 1. Write the function and formula. We have f of x equals x plus 2 and our standard derivative formula. Step 2. Find f of x plus h. We replace x with x plus h, So f of x plus h is x plus h plus 2. There's nothing to expand or simplify here. Step 3, find the numerator. We subtract the original function from this. Be careful to use parentheses. Distributing the negative, we get x plus h plus 2 minus x minus 2. The x's cancel and the 2's cancel. We are left with just h. Step 4, calculate the limit. F prime of x is the limit as h approaches 0 of h over h. Since h is approaching 0 but is never exactly 0, h over h simplifies to 1. The limit of a constant is just the constant itself. So f prime of x equals 1. Our solution is complete. This also makes sense geometrically. The function y equals x plus 2 is a straight line with a slope of 1. The derivative gives us the slope, and for a straight line, the slope is constant everywhere. Let's move to our third example. F of x equals the quantity x plus 2 squared. Step 1, write the function and formula. We have our function and the first principles formula. Step 2, find f of x plus h. This one requires careful substitution. We replace x with x plus h. So f of x plus h becomes the quantity x plus h plus 2, all squared. We can rearrange this to group the constants, x plus 2 plus h squared. Now we need to expand this trinomial squared. A good way to handle this is to let a temporary variable, let's say y, equal x plus 2. So if we let y equal x plus 2, our expression becomes y plus h squared, which we can expand easily using our binomial formula. Now we substitute back for y. This gives us x plus 2 squared plus 2 times x plus 2 times h plus h squared. This is our simplified f of x plus h. Step 3, find the numerator. We subtract the original function. The x plus 2 squared terms cancel out perfectly, just as we expected. We are left with 2 times x plus 2 times h plus h squared. Step 4, calculate the limit. We plug this into our formula. The limit as h approaches 0 of this expression over h. We factor out the common factor of h from the numerator, which gives us h times the quantity 2 times x plus 2 plus h. We cancel the h's, leaving the limit of 2 times x plus 2 plus h. Now we substitute h equals 0, giving us 2 times x plus 2. Distributing the 2, we get our final answer, 2x plus 4. Our final example for today. Differentiate f of x equals x times the quantity x plus 2 from first principles. The first step for a problem like this is to expand the original function first to make it a standard polynomial. This will simplify our algebra later. Distributing the x, we get f of x equals x squared plus 2x. So we are actually solving a new but equivalent problem. Differentiate f of x equals x squared plus 2x. Now let's follow our steps. Step 1 is complete. We have our function x squared plus 2x in the first principles formula. Step 2, find f of x plus h. Replace x with x plus h. This gives us x plus h squared plus 2 times x plus h. Now we expand the binomial and distribute the 2. This becomes x squared plus 2xh plus h squared plus 2x plus 2a. Combining terms, f of x plus h is x squared plus 2xh plus h squared plus 2x plus 2h. Step 3, find the numerator. We subtract the original function. Remember the parentheses. Distributing the negative, we get x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x. Notice the x squared and 2x terms cancel out as expected. This leaves us with 2xh plus h squared plus 2. Step 4, calculate the limit. We plug our expression into the formula. We have the limit as h approaches 0 of 2xh plus h squared plus 2h all over h. We factor out the common h from the numerator, giving us h times the quantity 2x plus h plus 2. After canceling the h's, we take the limit as h approaches 0 of 2x plus h plus 2. Substituting h equals 0, we get 2x plus 0 plus 2. Our final answer is f prime of x equals 2x plus 2. Again, if you verify this with the power rule, you will find the same result. Let's quickly recap what we've learned today. We started with the core concept of differentiation from first principles, which is derived from the geometric definition of the derivative as the slope of the tangent line. We used this formal definition. f prime of x is the limit as h approaches 0 of the difference quotient. We also learned a systematic 4-step process to solve these problems. First, write down the function and the formula. Second, expand and simplify f of x plus h. Third, calculate the numerator f of x plus h minus f of x. And fourth, factor and cancel h, and then find the limit by substituting h equals 0. A key takeaway is the expected pattern. All terms not containing h should cancel in step 3, and h should always be a common factor in the numerator in step 4. A key takeaway is the expected pattern. All terms not containing h should cancel in step 3, and h should always be a common factor in the numerator in step 4. By following these steps carefully, you can find the derivative of any algebraic function from its very first principles. Thank you for watching. If you found this tutorial helpful, please subscribe for more tutorials from Math Zone African Motives. See you next time.